This was the first application question. This is a great question to show the 7-step method for solving problems. First thing is you want to identify the target. So what is the question asking for? So quick description. This is a story of Galileo. It's a legend that says that he dropped a couple of masses of different mass from the Leaning Tower of Pisa to demonstrate that they would hit the ground at the same time. So I gave the information how much mass there was in one of those masses, making the numbers up obviously, and that it hit the ground at a speed of 33 meters per second. By the way, if you want, you can look that up, that the speed that it would likely hit by looking up the height of the Leaning Tower of Pisa and using your kinematics equations. Comes to a complete stop in 0.15 centimeters. So what's the stopping force exerted by the ground on the mass? That's the question that's being asked. So we're looking for the force of the ground, or the force upwards. I'll call it Fu, to remember that that's what we're looking for. Now, first step in this process is to draw a diagram and get a feel for what exactly is happening. So we're talking about the situation. I'll just draw a little sketch up at the top here, where the mass hits the ground and digs into the ground just a little bit in the process of stopping. Anytime something hits a surface and comes to a stop, one of those two things must be compressing. I assumed that it was the ground. It could also have been the mass. Maybe the mass compressed a little bit, because it has to travel a certain distance while it's changing its velocity from 33 meters per second to 0. So we're creating a tiny little indent here that's 0.15 centimeters. So it says in the question to draw a free body diagram, and of course there are 2 marks over here for drawing a free body diagram. So the free body diagram in this situation, you have to identify all the forces acting on that mass. So let's draw the mass in the center. It's not a cubic mass, but we're going to draw it that way anyway. I'll put the mass down here just for interest's sake. We know, because we're on Earth, that gravity is acting this way. So the force of gravity, let's make it a small g. And by the way, when you're drawing anything like this, it never hurts to write a little frame of reference. We also know that there's one other force acting here, and that is the stopping force that the ground is enacting on the ground, which I'm going to call Fu. So we know these are all the forces acting on the mass. What we have to figure out is what this value here is, knowing that the mass accelerates upwards because it's moving downwards and comes to a stop. It's accelerating upwards according to the net force acting on this. So what we really have is the upwards force and the gravitational force, summing those up, remembering that one is going to be positive and the other one's going to be negative, gives us the net force, and that net force results in the acceleration. So step 3 is to take the given information, which is that V1 is equal to, let's change our lighting here, equal to 33 meters per second. V2 equals 0. We're looking for the acceleration, or we don't know the acceleration, and we know the distance is 0.15 centimeters. Now, none of these is the tension force. We have to relate the tension force and the upwards force, so let's take this a little further. We know that the normal force, or the net force, is equal to the upward force. I've called this positive, the initial speed, so I've called down as positive. So I'm going to say that the upwards force is negative but we are looking for the difference between the two. So the upwards force, the difference between the upwards force and the gravitational force. For the moment, we'll just do it this way because it's easier to visualize. So the net force is equal to those two subtracted, and the final equation that's going to be useful to us is, of course, Newton's second law, which connects the net force and the acceleration. So let's start with the upwards force, and rearrange this equation. This is where we get into step 5, the algebra. We'll rearrange that equation to give us F up on the one side, or Fu, and that's going to be equal to the net force plus the gravitational force. Now, the way I'm getting around communication here is I'm not calling these vectors yet. I'm just looking for the absolute value. Now, Fg we know is mg. Fnet we know is equal to mass times acceleration. So I'm going to replace those two values. The mass times its acceleration plus the mass times gravitational acceleration. All right. Continue working with algebra and substitution. We also know there's one more equation, one more formula that I didn't put in, and that's the relationship between these 4 variables that will allow us to calculate the acceleration. I'm going to throw that, let's toss it down here on the side. So v2 squared equals v1 squared plus 2ad is the equation we want. We know this is going to be 0, so we're going to get v1 squared equals negative 2ad. Now, that becomes negative because it was a positive over here. We switched the v1, or we switched the 2ad over to the other side, so that became negative. What I'm going to do, again, is I'm going to take that negative, and I'm going to remember that I'm also looking at a negative acceleration, so I can just look at absolute values to get what I want here. I'm going to take that negative out, negative sign out, and I'm going to rearrange this for the acceleration. So the acceleration is going to be v1 squared divided by 2d. That's just algebraic rearranging of this equation here. So that I can now put in for this value here. So I'm going to write the upwards force is equal to, and I'll factor out that mass, v1 squared over 2d plus g, little g. Now we can put our numbers in. 2.5 kilograms times 33 meters per second squared over 2 times, and 15 centimeters, or 0.15 centimeters I should say, it's 0.00015 meters. Did I say that right? No, 0015, sorry. Now I've changed that to meters because everything is working in meters per second squared and meters per second, so I want to keep the units the same. Oops. And then I add little g. Okay, when I punch all that into the calculator, just for fun, for anybody who's interested in this kind of thing, I'll do it in the order that my calculator likes. Do the complicated part in the middle, 33 squared divided by 2 divided by 0.0015 equals, that's a big number. Adding 9.81 is not going to make a difference. Not really for our significant digits. And then that's everything inside the brackets here. And then I'm going to multiply that by 2.5. And that gives 907,524. We've got meters per second, meters squared per second squared up here, divided by meters, which is meters per second squared, plus meters per second squared, times kilograms, so our units work out. And again, 2 significant digits in the question, 2 significant digits in the answer, which gives us 9.1 times 10 to the power of 5 newtons. That's it.